Hydrogen embrittlement is a system property that is enhanced by material characteristics, mechanical stress under operation, and hydrogen availability on the component's surface. Hydrogen is produced in chemical and electrochemical production processes, especially during the pre-treatment stages and the galvanization process as a competing reaction to the metal reduction. Naturally, for the manufacturer, this raises the question of how to detect hydrogen embrittlement reliably during the manufacturing process. During the pre-treatment stage, the danger of hydrogen embrittlement is highest during the pickling process. In pickling processes, metal and metal oxides are dissolved in an acidic oxidation accompanied by a reduction in which hydrogen formation can be observed. The surface phase reaction of hydrogen formation can be understood from the Tafel, Vollmer and Herofsky reaction. As a result of the Vollmer reaction, hydrogen is absorbed at the phase boundary. This leads to recombination and formation of molecular hydrogen, which is also described by the Tafel reaction. Molecular hydrogen exits the phase boundary in the form of gaseous hydrogen and does not contribute to hydrogen embrittlement. If the hydrogen does not recombine, the phase boundary can be overcome and hydrogen diffuses into the metal structure. Detection of hydrogen embrittlement can be achieved by means of tension bending tests that are described in DIN 50969-2. Here, our automated tension bending test device using C-ring specimens has shown great results regarding the reliable and reproducible detection of hydrogen embrittlement. The diffusion of atomic hydrogen into the metal structure is positively affected by dislocation motions and tension gradients. Therefore, inhomogeneities in the crystal structure, such as notches and microcracks, enhance hydrogen diffusion and result in a local hydrogen enrichment. During the tension bending test, hydrogen dissolved in the crystal structure decreases the activation energy for dislocation movements after crossing the elasticity region of the material. Due to the dislocation motion in the tension bending test, atomic hydrogen is transported to areas of increased tension gradients, for example cracks and notches. Measuring the tension energy yields valuable information on the tension behavior of different materials. If atomic hydrogen dissolved in the crystal structure leads to hydrogen embrittlement, then a significant reduction in the energy needed to bend the specimen is observed. This is accompanied by a detectable brittle fracture. Rethinking tension bending tests. The tension bending test device developed by iChem Analytics connects different measurement procedures, specimen diversity, and newly generated material measures derived from the bending energy of the material to detect hydrogen embrittlement. Using the constant strain rate method, hydrogen embrittlement is detected within 180 seconds, allowing for online measurements during the production process.